Welcome all of you. Last time I gave you a brief introduction to what this course is all about. Just to summarize, this course is on plant-wide control, and before we can go over how to design effective plant-wide control systems for complex chemical processes with material and energy recycle, there are some essential things that we ought to know, and these essential things I would categorize into two items. Item number one, essential fundamentals of, or rather essentials of process control. And what I mean here is the most basic things in process control that you need to know as an operator or as an engineer, and also what you need to know is degrees of freedom of a process. So, the next two modules, degrees of freedom. So, the next two modules that we are going to cover, maybe next couple of lectures and another couple of lectures, would essentially focus on these two aspects: essentials of process control that an engineer must know to design effective control systems, and degrees of freedom of a process. These two concepts are quite fundamental, and we will spend some time on this over the next few lectures. So, let us get to essentials of process control. Essential process control fundamentals, that is the module that we are going to be looking at now. The outline of the breakup of this module is, first we are going to look at what process dynamics is. What do you mean by process dynamics? Given that in response to a change, an output variable responds in a certain way, how do you ensure that the output variable is kept where you want it to be kept? That is accomplished typically using feedback control. Now, in order to do feedback control, there are various controller algorithms. The most popular of them in the industry is the PID controller. So, we are going to talk in detail about PID controller, how you tune them. The PID controller requires some information so that it can be tuned well, and that information is gathered through process identification. So, we are going to cover the most basic process identification techniques that are popularly used in the industry. Since the focus of this course is practical industrial application, we are also going to look at a few common industrial control loops. These loops are typically flows, levels, pressure, temperatures and composition loops. How do you tune them? What are the typical characteristics of these loops, and so on and so forth. Then we will also look at a few advanced control schemes such as ratio, feed forward, cascade, override, valve positioning, optimizing control, and so on and so forth, which are employed routinely in industrial systems in order to achieve more effective or better control. Usually you would be studying single input single output systems in your basic process control courses, but in practice most practical systems are multivariable. What do you mean by multivariable? That means that it has got multiple inputs and it has got multiple outputs that need to be controlled, some may even float. So, we will also cover a little bit of multivariable control, because most practical industrial systems are multivariable in nature. So, that is the outline for this module. Coming to process dynamics. What is process dynamics? We all know dynamics. They say the situation is dynamic. What does it mean? It means situation is changing. So, this change over time is referred to as process dynamics. Specifically, what it means is, if you make a change to an input to a process, how does the output variable respond over time? That is referred to as process dynamics. So, to define it, I would say process dynamics is the time trajectory of a variable, specifically an output variable, in response to a change in an input to the process. There are several examples, and you need not be a control engineer to appreciate this. If you put a pot of rice on a gas, it takes about 15-20 minutes to cook. So, the cookedness of the rice is the output variable, the intensity of the flame is the input variable. Once the flame is on, rice starts to cook and it slowly gets more and more cooked, and finally it reaches its desired state of cookedness, and if you cook it for more than that, it may even get burnt. You also, every day we take a bath, especially in the winter season, using a geyser, and everybody knows that if I switch on the geyser right now, which is the input of the process, the water will become hot in say 5 or 10 minutes. So, it takes 5 or 10 minutes for the temperature of the water in the geyser to rise to whatever level I want it to rise to. Alright. So, these are some very simple examples that essentially show that an output variable changes over time in response to a change in the input. So, here is just a very simple example. The blue line is the input and the brown line is the output. So, let us say the input is the geyser is off, the heater power, the power of the heater, which is 0, and then when I switch on the geyser, its power goes to whatever it goes to, a 1 kilowatt or 2 kilowatts. Okay. And let us say the brown variable, which is the output variable, is the temperature of the water in the geyser. It is at ambient temperature, and as the geyser is switched on, what you have is the temperature, nothing happens to the temperature for a little bit, and then it starts to rise and it keeps on rising. It may keep on rising or it may settle down to final steady state value. So, this is an example of the dynamics of the output variable, which is the geyser water temperature in the geyser in response to the input, which is the power input to the geyser. Okay. So, essentially process dynamics deals with the systematic characterization of the time response of the affected variable to a change in the causal variable. The affected variable is also sometimes referred to as the output variable. The causal variable is also sometimes referred to as, or usually referred to as, the input variable. Okay. So, here is for example a distillation column. There is a feed to the column. Let us say it is an ABC mixture, A being the lightest component, B being intermediate boiling, and C being the heavy component, and you are doing a direct split. So, what that means is you are taking out the lightest component of the top and everything else that is heavier goes down the bottom. So, pure A is not pure A, nearly pure A is obtained at the top, and the B and C with some amount of A leave down the bottoms. Okay. So, for this process, the input to the column are the feed, the reflux into the column, and the reboil. All right. And the outputs from the column are, for example, how much distillate is coming out, how much bottoms is coming out, what is the temperature profile inside the column, temperature and composition profile, what is the purity of the distillate, and what is the purity of the bottoms. Okay. So, these are all output variables. In order to characterize your response in a systematic way, the inputs that are typically used are standardized. So, there are certain standard input changes, and in response to those standard input changes, you get typical responses. Okay. So, these standard input changes would, for example, be a step change, where you go from some level to another level and stay there. The input goes from some level to another level in a sharp step and stays there. You could also have a pulse, where the input goes up as a step and then comes back as a step after some time to the same value. You could also have an impulse, which is a sharp sudden change. Okay. And this mathematically speaking, the impulse is a Dirac delta function, but in practice you never are able to achieve a perfect impulse, or for that matter you are never able to achieve a perfect step. But nevertheless, what the step means is a very sudden change from one level to another level. An impulse, an example of that would be, for example, you inject a tracer into a flowing stream, that would be an impulse. Okay. Or that would be similar to an impulse, but not exactly the Dirac delta impulse. Okay. So, these are standard input changes, and you would give these standard input changes to the process and then observe the output. Now, there are certain basic transient response types. Okay. And it is like human beings can be categorized into different basic personality types. Similarly, no matter what the process, you give a change to the input, the output will typically fall into some basic response types, and it is these basic response types if you combine these basic response types, pretty much all the responses that are there possible can be, all the possible responses are some combination of these basic response types. For example, and these transient response types are these transient response types are typically solutions to ordinary differential equations. The simplest ordinary differential equations are linear with constant coefficients, time invariant. Here is an example. The example that I am talking about is a second order differential equation, and it is written over here. Here is another example. This is a first order differential equation, and you would see that if you give a step change to a first order system, the output would rise as an exponential, and we have not done Laplace transforms, but that is besides the point. So, you are giving a step change and the output responds as an exponential of the total change in the response from the initial value to the final value. The output changes by 63.2, about 2/3 of the response gets completed in one time constant. Okay, I think I need to explain this. Okay, well, so here is the differential equation, maybe. So, here is a first order differential equation, the simplest differential equation, dy by dt plus y is equal to kp times u, and y is a function of time, u, the input, could also be a function of time. Now, if the u is a step, this tau p is known as the time constant of this first order differential equation. It is called the time constant. Now, if you give a step, if ut is a unit step, if ut is a unit step, then if ut changes as a step, it goes from 0 to 1, 0 corresponding to the rest state of the system, 1 corresponding to a unit change, then the output of this differential equation y would change like this. Okay. This is called the final steady state, where the rates of change are 0. So, if you put dy by dt to 0, because at the final steady state dy by dt should be 0. If I set dy by dt to 0 at the final steady state, if ut is 1, you will have y at time t tends to infinity is kp. So, that is what you have, this is kp, and if you look at the solution of this differential equation, what you also have is that at t is equal to tau p, y t is equal to 0.632 of kp. What that essentially means is that 63.2% of the overall response gets completed in one time constant. Similarly, about 95% of the total response gets completed in 3 time constants. So, in one time constant, if this is the total response, 2/3 would be about here. This would be one time constant. If you take 3 time constants, which would be about here, about 95% of the overall response would have completed. So, this is a first order, this is the response of a first order system to a step change. By default, we are going to look at step changes as our standard input change. We are not going to look at pulses or impulses. Okay. So, this is the response of a first order process, of a process that is described by a first order differential equation. If you connect first order lags in series, well, we will get back to, here is my process, which is a first order lag. A first order ordinary differential is also sometimes referred to as a first order lag. You have your input and you have your output. Okay. if this output is further going into another first order lag, and if this output is further going into another lag, and so on so forth, what you have is lags in series. Let us say there are n lags in series. Then if you look at the output from the nth lag, if the input change is a step, if u changes as a step, y n would change in this case something like an S shape. Okay. So, when you see an S shaped response, that essentially can be described by n number of lags in series. So, if you connect first order lags in series, the output in response to a step change in the input changes as a sluggish S response. Looked at conversely, if you are looking at a response that is S shaped, it can be described by n number of lags in series, right. You could also have a second order differential equation, the output would be oscillatory. First order lags in series, S shaped or a certain exponential rise, these are very smooth responses. Sometimes what you see is the response of the output to a step change in the input may be oscillatory. These oscillations may die down in time as shown in the first subplot. These oscillations may be sustained, they just keep going on and on and on. Alternatively, these oscillations may actually blow up in time. Okay. So, the first case is usually referred to as damped oscillations. Sustained oscillations, you are at the limit of instability, and if the oscillations are blowing up, that means your system is unstable. We will talk a little more about instability, but these are some of the typical oscillatory responses that you see in practice. In order to get oscillations, the system has to be under damped second order at least. Okay. That is because maybe it is not appropriate to go into the theory of differential equations. So, let us just say, so here is a second order differential equation, the simplest type, and this guy tau is again referred to as the time constant. This fellow psi or eta, whatever the symbol name may be, is typically referred to as the damping coefficient. Okay. This is referred to as the gain, process gain. Okay. So, now this damping coefficient could be less than 1, 1, more than 1, 0 or even less than 0. Okay. So, I have just drawn some responses for different values of this damping coefficient, and what you would see is if the damping coefficient is, let us say 5, you get a very sluggish response. As the damping coefficient is decreased, damping coefficient 1, the response is a fast exponential rise to the final steady state value. As the damping coefficient goes below 1, you start getting oscillations. The magnitude of these oscillations increase as the damping coefficient goes down. Okay. At a damping coefficient 0, the oscillations are sustained, that means they do not die down. If you go below 0, these oscillations will actually blow up. Okay. So, the damping coefficient actually characterizes your second order system. If the damping coefficient, what is the symbol that we have used here? If the damping coefficient is greater than 1, the system is known as overdamped. If the damping coefficient is equal to 1, the system is called critically damped. If the damping coefficient is less than 1, it is called, forgive my handwriting, it is never good, that is why I use these presentations, because okay. So, if the damping coefficient is less than 1, you have an underdamped system, then underdamped second order systems will show oscillations. Okay. If you go into the theory of differential equations, what you will find is the left hand side can be described, the characteristic equation has got roots. When epsilon is greater than 1, both the roots are real and not equal. At epsilon equal to 1, the roots are equal and real. As epsilon goes less, as the damping coefficient goes less than 1, these roots become complex conjugate pairs, and for oscillations the characteristic equation has to have at least one set of complex conjugate pairs. Okay. These oscillations are because the roots are complex conjugate pairs. Alright. I think that is about all that I want to say on this. Basic transient response types, a pure integrator. What is a pure integrator? A pure integrator is nothing but, well, a pure integrator. So, you have the input and you have the output. So, if the input goes up as a step, the output y would be integral of u dt. So, if u goes from 0 to 1, well, the output is just going to increase as a ramp, and the slope of that ramp is equal to the gain. Okay. What is an example of a pure integrator in process situations? An example is tank level, and just to explain it a little bit more. So, consider a very simple liquid tank. Liquid is flowing in, liquid is flowing out, and you got some hold up, some liquid level in the tank. Okay. You have got a valve at the inlet flow, and you also got a valve at the outlet flow. Now, if the level is constant, that means the level is not changing, that indirectly implies that the inflow is exactly equal to outflow. Okay. So, at steady state, flow in is equal to flow out. Okay. So, this is F in, this is F out. Now, let us say at time t equal to 0, the flow in goes up slightly as a step. What will happen to the level? Flow out is maintained at the same value as it was at before. So, flow out remains at the same value, flow in goes up, the level will slowly start to rise and it will keep on rising, right. This is an example of a pure integrator in chemical processes, levels in liquid tanks. Okay. What does it mean? What implication does it have? What it means is, the level, unless you balance the flows, the level is either rising or decreasing. Such variables are also sometimes referred to as non-self regulatory. So, liquid level in a tank is a non-self regulatory variable. What does it mean? It means the liquid level won't regulate itself. You have to control the level so that the tank doesn't overflow or run dry because the flows are not matched, right. So, what that essentially implies is all non-self regulatory variables in a process must be controlled, because they won't regulate themselves. So, you have to adjust the input and or the output or some variable, so that in this particular example case where the non-self regulatory variable is the liquid level, so that the liquid level does not reach an unsafe condition. For example, the tank overflowing or the tank running dry. Why is the tank running dry an undesirable situation? Because there is a pump that is pushing the liquid out. If there is no liquid to be pumped, the pump is going to get burnt. So, that is something that is not desirable. So, all liquid levels in a process must be controlled, okay, must control all liquid levels in a process. Here is an inverse response. You give a step change, the output goes in the wrong direction first, in the other direction first, turns around and then goes back up. So, the initial direction of response is in some sense the wrong direction. This is also sometimes referred to as wrong way behavior. Wrong way behavior. Another common example of inverse response in chemical processes is the level inside a boiler. An example of inverse response, a process example of inverse response. Consider a distillation column. So, you got a distillation column, you got the reboiler where you are putting in steam, the liquid in the reboiler boils and this reboiler is sent, this reboil is sent back into the column, and of course, some of the liquid is drawn out, and in the column there are trays. Okay. There are trays in the column and down comers. So, there is liquid on this tray which is actually flowing down and collecting in the bottom sump. This is the bottom sump. Let us say you increase the reboiler duty, let us say you increase the steam flow. In other words, what I am saying is you open the steam valve. So, more steam is going into the reboiler, because more steam is going into the reboiler, this flow would increase, the amount of vapor going into the column would increase. So, you expect, because the amount of vapor that is going into the column is increasing, you would expect that this level should go down, because it is this liquid that is getting boiled, right, that is getting reboiled. Okay. So, you expect that if the steam is increased, the level inside the reboiler should decrease. What you would find is that actually what happens is, if you increase the steam flow, the level actually first increases and then decreases. It shows actually an inverse response. All right. Why is this happening? It is happening because the vapor that is going into the trays above actually pushes more of the liquid down. Okay. So, the level rises in the bottom sump. Also, as the liquid is getting more heat, there are more number of entrapped bubbles in the reboiler, and those entrapped bubbles cause the interface to rise up. Okay. So, because of these two things, initially the level seems to rise, and then of course, later on, because liquid is getting removed at a faster rate, the level goes on to decrease. Okay. So, this is an example of an inverse response. Another example would be probably a thermometer. So, if you have a thermometer with alcohol in it as the temperature sensitive fluid, let us say the thermometer is made to come in contact with a hot fluid. Now, you would expect, because the thermometer is going to be hotter, you would expect the level or the alcohol in the indicator, its level should rise up because the temperature is hotter. But what actually happens is, the level the metal, because it is a good conductor, gets heated up rather quickly. So, it expands. Because it expands, the alcohol level actually initially drops, then of course, the alcohol also gets heated, and then the alcohol level, because of the heating, goes on to rise. So, if you look at the response of a alcohol thermometer, if the input temperature is rising like this, the dynamic response of the temperature indicated by the sensor, by the thermometer, would actually look something like this. Of course, finally it will become the same as the actual temperature, because everything will come in thermal equilibrium. This is the inverse response. Okay. So, this is another example. By the way, the level is non self regulatory. This example, the temperature actually, the output actually settles to a final value. So, it is self regulatory. Okay. But nevertheless, the inverse response or the wrong way behavior is there. Another example of wrong way behavior in process systems is packed bed reactors. What happens is, in packed bed reactors, because of the conductivity of, because heat can get conducted backwards through the packing. Sometimes what you have is, if you are increasing the temperature of the feed, you would expect the temperature of whatever is coming out of that packed bed reactor to also increase, but it can show wrong way behavior. This has been studied quite extensively by Luss and co-workers. So, wrong way behavior also occurs in packed bed reactors. Okay. So, these are just some of the examples of where you see inverse response in process systems. Getting back to our presentation, so example of a temperature measurement in a glass tube mercury well thermometer. Basic transient response times, pure dead time. This pure dead, so you make a change now, nothing happens at the output. After some time, output goes to the same value as the input. So, there is a pure dead time, and this is because of transportation lags. There are also unstable responses. One example that we have already come across is an oscillatory response where the oscillations are blowing up. You could also have a non-oscillatory response where the temperature where the output just keeps increasing, there is an exponential rise in the temperature. This can happen in reactors. A non-oscillatory exponential rise in temperature can happen in reactors. It is like the reactor catches fire, the temperature just keeps shooting up. Okay. So, well that is that. It is called a runaway reaction, Bhopal gas tragedy. That was a runaway reaction that happened because water seeped into the methyl acetate gas tank, and methyl acetate and water react exothermically. So, what happened was, because water got into the tank, because it leaked back, temperature of the cold tank started to rise, and as the temperature of that cold tank was rising, reaction went on faster. So, more and more heat was released, and so the temperature of that tank kept on increasing ever faster, exponential rise in the temperature, and finally the gas just burst out, and you had that tragedy on December 4th, I think, or maybe December 3rd, 1984, which it was in the news recently. Okay, so that's an unstable exponential rise in temperature. It is called a runaway reaction. So, that was a runaway reaction which actually falls in the category of a non-oscillatory response of the unstable type. Coming back to process dynamics, we are trying to characterize the response of an output to a change in input. So, we have studied the basic response types, a first order lag, a pure dead time, a second order response which could be oscillatory, which could be non-oscillatory, unstable responses that are oscillatory or non-oscillatory, and so on and so forth. Now, regardless of what type of a system you are looking at, whether it is an aerospace system or a chemical system or a mechanical system, the dynamic response of any process can typically be well represented by a combination of these basic response types. Coming back to chemical processes, because there are very large holdups in our processes, our processes are very sluggish, and the S-shaped curve is a very common response to a change in the input. Just to clarify again, so if you give a step change, many a times in chemical processes the response would be nothing happens for some time, and then you get a slow rise, and finally the response settles to a final steady state value. Okay. So, these exponential n lags in series are many a times represented as a combination of nothing happens for some time is a dead time, and then an exponential rise. Okay. So, a first order plus dead time dt, dead time. Okay. So, these first order plus dead time models are very commonly employed to represent the dynamics of many chemical systems that show this sluggish S-shaped response. So, all transient responses can be well represented by combining basic response types, and one such combination which is very commonly employed in chemical process modeling is first order plus dead time. So, in a first order plus dead time model, nothing happens for the dead time, and then there is an exponential first order rise to the final steady state, and the response rises to 63.2%. If this is 100%, the response rises to 63.2% in one time constant. So, overall the response takes theta plus tau units, time units, to complete about 2/3 of the whole way, right. So, this is very commonly employed, routinely employed in chemical process modeling. Inverse response, how could you represent an inverse response that we talked about? Well, it can be represented using two lags in parallel. Consider So, you are giving a step change at time t equal to 0. Okay. One of the lags is a sluggish first order response with large gain. So, what happens there is it is a sluggish first order response with a large gain. Okay. The other lag is a fast transient response in the opposite direction, that is negative gain. So, it is fast, but small negative gain. So, you get a fast response, but a small negative gain. When you add these two up, the overall response would look something like this. You know, this difference would be whatever this gain is, right. So, this is how an inverse response is modeled as lags in parallel. Okay. In process dynamic parlance, if you are familiar with Laplace transforms, which you should be, an inverse response corresponds to a right half plane 0 in the open loop transfer function. Okay. But that is besides the point. I think conceptually you can clearly see that if you got a sluggish large gain first order response and a fast small gain in the small negative gain response in the response, you sum the two up, what you will get, the output would be an inverse response. So, getting back to our presentation, that is what we are showing. So, the inverse response, you have got this minus this, okay, and then what you get is an inverse response. All right. These are just two examples where I have used different values for the gains and the taus to show that you can have inverse response in that direction or in this direction. So, different values of gain and time constant for the first lag, different values of gain and time constant for the second lag, and what you get is an inverse response in the with a negative with a steady state negative gain, and here you get an inverse response with a positive steady state gain. All right. Now, we come to feedback control. Getting back to the previous lecture that we had, the objective of our operation, we must operate the process such that the operation does not create an unsafe situation, is never created. And why do we want to avoid unsafe situations? Because we are dealing with chemicals that are hazardous in nature. A little bit of gas leak and n number of people can perish, one explosion, n number of people perish. So, safety is of prime importance. You want to operate your process in a safe manner. Stability, why is stability important? Because if the system is unstable, typically you will end up in a safety hazardous in a hazardous situation. And last but not least, economics, you are operating the process actually to make money. So, you want to ensure safety, stability, and finally, you want to run the process in such a manner that you make profit. Okay. So, in order to ensure safety and stability, this typically boils down to maintaining key process variables at or near design conditions. What does that mean? For example, you would like to operate a reactor at its design operating temperature. You would not appreciate too large variations or large excursions in the reactor temperature from its design operating temperature, because it could lead to a runaway, for example. Okay. Now, in order to maintain key process variables at near design conditions, the variable may go away from its design condition because certain inputs to the process changed, there are certain disturbances and so on and so forth. Now, in order to maintain it at its desired value, you can change some inputs. So, if the reactor temperature is increasing, well, increase the cooling of the reactor if it is an exothermic reaction, and the increased cooling will bring the reactor temperature back to its set point. So, this is the basic idea behind feedback control. You adjust a process input to bring back a deviating process variable back to its desired value. The desired value is often referred to as the set point. So, you have the process variable measurement. In feedback control, what you are doing is you are looking at the measurement, and if it is deviating away from the set point, based on those deviations you are deciding by how much you should change the input in order to bring that deviating variable back to the set point. And this procedure that is used to translate the deviation in the process variable to an adjustment in the input variable, which is also referred to as the manipulated variable, is called the control algorithm. How do you translate the deviation in the process variable into a change in the input to the process into the manipulated variable? That is done by a control algorithm. It could be very simple. If temperature is increasing, for example, this air conditioner, the thermostat, if temperature has increased beyond a certain limit, switch off the compressor, or rather switch on the compressor. If temperature has gone down beyond a certain limit, switch off the compressor. So, this is a very simple algorithm, it is a control algorithm, alright, which is called on off control. The compressor is either on or off depending on where your temperature is. The control that is implemented or that is most popular in industry is more sophisticated than this on off control example that I gave you, very rudimentary. What you have is, you have a process, you have different sensors in the process which are indicating flows, temperatures, pressures, compositions, molecular weights, melt flow index, and so on and so forth. So, there is a sensing element. Whatever be the sensed signal, for example, it could be a slight change in the stress that a sensor sees. This mechanical or whatever sensed signal is converted to an equivalent electrical signal using a transducer. A very common example of a transducer is a Wheatstone bridge. Now, this transducer will give you an electrical signal which is, say for example, in millivolts or in volts or milliamperes or whatever. Now, for standardization, the input to a controller is always between 4 to 20 milliamps, and the output from the controller is always between 4 to 20 amps. Why do you want standardization? So that every manufacturer is manufacturing the same type of controller. So, you can buy your controller from here, from there, from wherever, and you can be assured that it will take a kind of input and it will give you a kind of output, and it is standardized across everyone. Okay. So, the transducer gives a signal which may be in volts, millivolts, etc., etc., but this signal needs to be converted into a signal that can be taken by the controller. So, the transducer electrical signal is converted to a 4 to 20 milliamp signal by the transmitter. Okay. The controller does its calculations and then it outputs a 4 to 20 milliamp output signal. Okay. Now, in chemical processes, the manipulated variable is typically some flow somewhere. For example, you would be manipulating the steam flow into a heat exchanger in order to keep the temperature of a process stream at its desired value. Alternatively, you may be adjusting the cooling water flow in order to cool a stream, and so on and so forth. So, typically what gets adjusted or manipulated in order to hold an output at its set point is some flow somewhere in the process. Now, how do you adjust flows? Using control valves. How do you move control valves? Well, how do you move a control valve? Well, typically a control valve will have a spring, a diaphragm, and then air is pressing against that spring. If you increase the pressure, of the air, the valve closes. If you decrease the pressure of the air, the valve opens. Okay, so there is this instrument air that is supplied to all valves, and this air, by varying the pressure of this air, you are changing the position of the valve, and as the position of the valve changes, the fluid flow rate changes, and this is what is the manipulated variable. Okay. So, now the output from the controller is a 4 to 20 milliamp signal. What you need to do is convert that to an equivalent pressure signal, which is the pressure being exerted by the instrument air against the valve. Okay. So, this is done by an I to P converter, a current to pressure converter, and again the output of I to P converters is standardized. It is between 3 to 15 psi gauge. So, the instrument air, so 4 milliamp for example may correspond to 3 psi and 20 milliamps may correspond to 15 psi. Okay. So, the I to P converter gives the desired pressure on the air, and because the air pressure then changes, the valve actually moves. It either opens or it closes. The valves can also be of two types. It could be fail open. Let me write this down. It could be, valve could be fail open. That means if the air supply fails, the valve will open fully, it would be 100% open. It could also be fail close. That means if the air supply for some reason is taken away, fails, then the valve will fully close. Okay. That is just a matter of where the pressure is being applied and how the spring is oriented. If the spring is like this and air pressure is applied like this, well, valve will close as the air pressure is applied. If the air pressure fails, the spring will make the valve fail open. If the spring is this way, and the air pressure is being applied this way, well, as you apply the air pressure, valve actually opens. Okay. And so, it is a fail close valve. Okay. Where do you use in process situations fail open and fail close valves? Well, this is determined by safety, and an example of that would be, for example, you got steam going into a reboiler in a distillation column. Okay. You would like this valve to be what? If the instrument air fails to this valve, what would you like? Should the steam flow become maximum, fully open, or should the steam flow go to 0? Well, safety dictates if the air supply is failing, the valve should actually close, so that too much heat is not supplied to the reboiler and it does not get burnt, right. So, this valve should be fail close. If the air supply fails, the valve should close. What is an example of a fail open valve? Okay. If you take the condenser of the column, you got a condenser in the column which is taking hot vapors, condensing it, putting it into a reflux drum, and some of it is given back to the column, the other is taken out as distillate. If you take a condenser to the column, this cooling water valve, what should it be? Fail open or fail close? Well, if the air supply to the valve fails, what would you like? You would like that whatever hot vapor is coming, it should get condensed no matter what. In order to ensure that, this cooling water valve must fail open. If the air supply fails, cooling water is at max, so that the hot vapor that is coming gets condensed regardless of whether the air supply is there or not, right. So, this valve should be fail open. So, the processing situation determines what type of a valve you will have. You have the process, there is a sensor that is measuring the output, this is the measuring element, through the this includes the transducer. This is saying what the output is, what my temperature, flow or pressure is. You would like that temperature, flow or pressure to be at a certain set point. The difference is the error. This error goes to a controller, which are typically PID controllers. The controller outputs a signal which goes to the final control element, which is typically a control valve, and because the control valve moves, the input to the process changes, and hopefully if you have got everything right, the change in the input would be such that deviating y will be brought back to normal, brought back to its desired value. Okay. So, this is just a block diagram of a feedback control loop. A very common example of feedback control is, suppose you go to take a bath, you got the hot fluid coming from, hot water coming from the geyser, you got the cold water coming from from the tank, overhead tank. You want the temperature of the water to be comfortable, maybe 37-40 degrees Celsius. Okay. So, what you would do is, you would open the cold water and then open the hot water and then adjust the two valves such that the temperature of the mixed stream is what you would like it to be, so that you take a comfortable bath. This is an example of feedback control. Your body is sensing what temperature the water is. If it is uncomfortable, if it is too hot, you will either increase the cold water flow or you will decrease the hot water flow. If it is too cold, you will increase the hot water flow, right. So this is one example. Another very common example is driving a cycle. Driving a cycle would be feedback. Your balancing a cycle is essentially feedback control. It goes this way, you adjust this handle such that it remains straight. So, depending on which way it is going, you will make an adjustment in your handle position so that it remains balanced. So, balancing a cycle is also an example of feedback control.